So, what happens when you take two of the biggest tech revolutions of our lifetime and just smash them together? I'm talking about artificial intelligence and quantum computing. Today, we are going to dive into this really fascinating paper that figures out a way to combine their power while also fixing one of their biggest, thorniest problems.
And that brings us right to the heart of the matter. It's the big question, isn't it? We all want AI that's smarter and more helpful, but it always feels like the price we pay is our own personal data. It's this awful trade-off. So how do we get the best of both worlds? Well, it turns out the answer might just be hiding in this really clever mix of quantum physics and decentralized computing.
Okay, let's get into it. And to start, we really need to understand the two massive hurdles we're trying to clear here. You've got AI's endless appetite for data on one side, and on the other, the very real, very practical limits of the quantum computers we have today.
So you can see the tension here, right? On one hand, the promise is just huge. We're talking AI that can outperform humans and quantum machines that could solve problems we currently think are impossible. But then there's the flip side, the peril. AI's hunger for data creates these enormous privacy risks, and the quantum computers we actually have right now, these things called NISQ devices, they're just not ready for the big leagues. Noisy and intermediate scale means they're small, they make a lot of mistakes, and they're totally unable to handle these giant data sets by themselves.
So how in the world do we fix this? Let's look at the first piece of this puzzle. It's a concept from the good old classical AI world that gives us a decentralized solution. It's basically a way to learn, without ever having to peek at the raw data itself.
And that solution is called federated learning. The whole core idea is right there in the definition. You train the AI model across a bunch of decentralized devices. Think millions of different smartphones. But the private data itself never, ever leaves those devices. The learning comes to the data, not the other way around.
And I love this analogy because it just makes it all click. Imagine you want to create the world's greatest cookie recipe. Now, instead of making everyone send you their secret handwritten family recipe cards, you just send out a basic starter recipe. You ask everyone to bake a batch, make it a little better, and then tell you how they improved it. Then you just combine all that feedback to create one ultimate master recipe. You get the collective wisdom without ever seeing a single secret ingredient.
So let's walk through how this actually works. First, a central server cooks up a general global AI model. That model gets sent out to all the local devices, like your phone. Then, your phone uses its own local data, your photos, your messages, whatever, to train that model and make it a little smarter. But here's the magic part. It only sends the improvements back to the server, the learned updates, never ever your actual data. Finally, the server gathers all those tiny updates from thousands or even millions of devices and merges them to create a brand new, much smarter global model. And then the whole thing just starts over again. Okay, so we've got a way to train AI that keeps our data private. Fantastic! Now, let's bring in the quantum part. This is where we get to combine the privacy of federated learning with the mind-bending potential of quantum mechanics.
And this takes us right back to that NISQ problem. We have these small, promising, but kind of flaky quantum computers. You can't just dump a giant data set on them. But what if you use that federated setup to spread out the work? What if you could give each little quantum computer just a tiny, manageable piece of the puzzle to work on? This isn't just a clever idea. It's pretty much a necessary strategy given the hardware we have today.
The solution the researchers came up with is this really elegant hybrid model. Think of it like a tag team. First up, you have a powerful, already trained classical AI, in this case one called VGG16, which is an expert at recognizing images. It does all the initial heavy lifting. It'll look at a photo of a dog and boil it down to its most essential features, squishing all that info into something called a data vector. It's basically a super condensed summary in number form. Only then is that little bit of distilled information handed off to the quantum computer for the final, really tricky classification step.
So what exactly is this quantum part of the tag team? It's called a variational quantum circuit, or VQC. The easiest way to think about it is like a tiny quantum neural network. And the key thing is that it has these adjustable parameters. You can picture them as little tunable knobs on a machine. A classical computer helps to tweak these knobs over and over and over. Every little tweak is like a tiny lesson, and after thousands of tries, the quantum circuit literally learns how to get better and better at its job.
Now, this all sounds amazing on paper, but does it actually work in the real world? Well, let's get to the results and see the proof. And in this case, the proof is literally in the pixels. So, the researchers put their framework to the test on two classic image challenges. The first, telling the difference between cats and dogs, and the second, distinguishing between airplanes and cars. These are like standard obstacle courses for seeing how well an AI can, well, see.
And here we go. The results for the cats versus dogs test. And honestly, these numbers are staggering. Their federated quantum model hit 98.7% accuracy. And the traditional model, the one where all the data gets hoovered up into one central place, 98.75%. I mean, come on. That difference is basically a rounding error. This is the big reveal. We get all the benefits of privacy and distribution without losing any meaningful performance.
This chart just makes it so clear. You can barely see the difference between the bars because, for all practical purposes, their performance is identical. And that's the huge takeaway here. We got the same incredible accuracy without ever needing to centralize the data. We protected user privacy, we distributed the massive workload across smaller machines, and we didn't have to sacrifice performance to do it.
And hey, this wasn't just a one-hit wonder. They ran the same exact test on the planes versus cars dataset and got the same result. Over 93% accuracy. Again, basically a perfect match for the non-federated model. This proves the whole method is consistent and really robust, no matter what images you throw at it.
You know, the researchers themselves summed it up perfectly in their paper's conclusion. This isn't just a small step forward. It really does pave a new direction. It shows us a realistic path to building AI systems that aren't just powerful, but are also secure, scalable, and most importantly, respectful of our privacy.
Which really just leaves us with this final, tantalizing question. For so long, it felt like we had to make a choice. Do we want smarter AI, or do we want our privacy? But what this research suggests is that maybe, just maybe, that was a false choice all along. Maybe the future of AI really can be all three: incredibly powerful, deeply private, and distributed.